In this lesson, we will be examining the periodic properties of trig functions. This is an important objective because it will help us to understand and use this concept to find exact values of trigonometric expressions. It will also help us as we begin graphing these trig functions in order to visualize the periodic nature of each of these functions. Let's go ahead and look at some of these graphs. Let's look at the sine graph. Notice how the pattern repeats. It oscillates. This is a sinusoidal graph. The pattern repeats over the same interval. So if we start here at 0, the function rises up, and then it drops down through pi, and then comes back to 2 pi. If we go through the same pattern, you rise up from 2 pi, drop back down through 3 pi, and then we end up back in the same place at 4 pi. The period of the sine graph, you can see, is 2 pi. So every interval of 2 pi, the pattern repeats. Thus, we can write this expression. The sine of 2 pi, or the value of the sine of 2 pi, plus any number of those periods, will always be the same value. As you can see here, at 0, it is 0, at 2 pi it is 0, and at 4 pi is 0. So we know that the period of the sine graph repeats every 2 pi. Now let's look at the cosine graph. The cosine graph looks a little bit different, but it's still a sinusoidal graph in that it oscillates, it repeats. So if you picture this part of the graph coming from 1 down to -1 and up to 1, the graph will then repeat itself, drop back down to -1 and come back up to 1. If you'll notice, the period still goes from 0 to 2 pi. So the value of the cosine at 2 pi plus any number of those periods will always be the same value. Let's move on and look at its reciprocal graphs. Here we have the cosecant and secant graphs. These are the reciprocals, remember, of the sine and cosine. Notice that our period is still the same. From 0 to 2 pi, we have what looks like an up u, and then here an upside down u. If we were to continue on, it would repeat, like down here on our secant graph. It's just in a little bit different location. But the interval goes from 0 to 2 pi. Down here, if we look at our intervals, we can still go from 0 to 2 pi without repeating. And then after 2 pi, we would then start repeating again. So our intervals for the sine, the cosine, the cosecant, and the secant will always be 2 pi. Let's look at our final trig functions. That would be the tangent and the cotangent. This one is a little bit different. If you'll notice this graph here between -pi/2 and +pi/2, that graph then repeats. Same thing with down here. If we go between 0 and pi, it now repeats. So the interval here is not 2 pi, the interval is just pi. The distance between -pi/2 and +pi/2 is pi. And then you can clearly see that down here. Let's summarize. So a periodic means that it recurs at regular intervals. A periodic function is any function whose value repeats after the regular addition of a period to its independent variable. So we just need to make sure we understand these periods. For sine, cosine, and its reciprocal functions, the period is 2 pi. For tangent and its reciprocal function, the period now is just pi. Let's apply this and try some examples. For these examples, we want to find the exact value of the expression using the periodic nature of these functions. So what does that mean? That means we're going to pull full periods out of here to see what's remaining, and then we can determine the value of the trig function. So 9 pi/4, this is sine. Sine has a period, remember, of 2 pi. Now what we want to do though is we want to pull out periods of 2 pi. We have a denominator of 4. So in order to get 2 pi, we have to write that as 8 pi/4. That simplifies to 2 pi. So if we pull 8 pi over 4 out of this, what do we have left? We have just pi over 4. So ultimately, we need to find the sine of pi over 4. Well, the sine of pi over 4 is just root 2 over 2. Let's go ahead and look at the secant of 540 degrees. The secant is a reciprocal function to the cosine. So we know that it has a period of 2 pi. So what we can do here then is pull out 360 degrees. And what do we have left? We have 180 degrees left. So now we're just trying to find the secant of 180 degrees. Remember that the secant is just the reciprocal of the cosine. So we're really trying to find the secant, which is 1 over the cosine of 180 degrees. The cosine of 180 degrees is -1. So our answer here is -1. Let's go to the tangent. So what is the period of tangent? Remember that the period is just pi here. So we need to pull out intervals of pi. In this example, because our denominator is 4, an interval of pi would be 4 pi over 4, because that is equal to pi. Based on this period then, 4 goes into 33 approximately 8 times with a little bit left over. So we can pull out 8 times 4, we can pull out 32 pi's over 4. And then we get a remainder of 1 pi over 4. So all we have to do then is determine what the tangent is at pi over 4. And we know that the tangent at pi over 4 is y over x, or root 2 over 2 divided by root 2 over 2, which is just 1. Let's look at our final example. If you'd like to pause the video and try this one on your own, go ahead. Okay, the secant of 420. Well, secant is a reciprocal function, again, for cosine. So we're going to pull out of this an entire period, which is 360 degrees. What do we have left? We have 60 degrees. We're trying to find the secant then of 60 degrees. Well, the secant, remember, is 1 over the cosine of 60 degrees. The cosine of 60 degrees is just 1/2. So we can't leave our fraction as 1 divided by 1/2. Instead, we would need to do 1 times the reciprocal of 1/2, which is 2 over 1, and 1 over 1 times 2 over 1 is just 2. And that's how we can use the periodic properties of trig functions to help us find the exact values in a more simple, efficient way. That concludes our lesson today on periodic properties of trig functions.